ATS EVS 105 students. Welcome to the lecture that's going to continue on our chapter in the textbook. We're going to be talking now about climate feedbacks. You know, in the last module, we learned about these ideas about these climate models, these big numerical models that run on supercomputers, take weeks to run, etc. A valid question to ask would be, why? Why do we need all that? Couldn't we just compute something like the future mean global temperature based on whatever the factors are that we're changing, like the greenhouse gas concentrations and so on? I mean, we've had simple conceptual models like this really almost all semester. Isn't our situation when we change the greenhouse gas concentrations basically just a modified version of this conceptual model? Well, yes and no. I mean, I like the idea that we're going to take the greenhouse gases and we're going to modify their concentrations, and that will change the amount of long-wave radiation that is coming down from the sky back to the surface of the Earth. That's true, and I like the idea that that's going to increase the temperature of the Earth, which will, by Stefan Boltzmann law, increase the amount of long-wave radiation the surface is emitting upward and so on. But it gets kind of a lot more complicated than that because of other things that will change when you change the temperature. For example, increasing the temperature might also change, say, the surface albedo of the Earth. For example, when you increase the temperature, you're going to start melting some ice. And ice has a very high albedo. When you melt it in exposed bare ground, it's going to have a lower albedo. That'll change the amount of radiation being reflected by the surface of the Earth, and suddenly all these numbers change. It's going to have consequences for the whole energy balance. And that's hard. I mean, that's how much ice are we talking about? How fast will that ice melt? And so on. It's a complicated question. I mean, I'm going to use a series of these kinds of diagrams to illustrate how we get into different kinds of feedback loops that are going to be making changes to our simple ideas about our simple conceptual models of how the radiation and energy balance should work. I mean, in this case, if we start at the red circle there, that's our initial warming just due to enhancing the amount of greenhouse gases in the atmosphere. Well, that would mean that the ice would melt, and or at least some ice would melt, or snow would melt or something, which would then result in the albedo of the Earth decreasing, which would mean that more solar energy is going to be absorbed by the surface of the Earth, which will make the surface of the Earth even warmer. But notice that that closes a loop here. See, the warmer now we've made the surface of the Earth, even more ice will melt, which will make the albedo even lower, which will mean even more solar radiation will be absorbed, which means even more warming, and we've got a positive feedback going here. A positive feedback amplifies the original change. Our original change of increasing the temperature of the Earth is now magnified or amplified by this positive feedback. This particular one is called the ice albedo feedback. There's other ways that these kinds of feedbacks could happen that are not about ice. For example, let's start another one here with this new red circle here. What if we increase the amount of carbon dioxide in the Earth's atmosphere? Well, one of the things that will happen is we'll have more vegetation, there'll be more plants, because they do thrive when there's higher carbon dioxide concentrations in the atmosphere. But that will extract some carbon dioxide from the atmosphere, which means we'll have fewer plants. But if you have fewer plants, then the amount of carbon dioxide in the atmosphere goes up, there's fewer plants consuming it, and then we get more plants, and we've diminished the original effect. We started off with adding carbon dioxide, but now we ended up reducing the amount of carbon dioxide. This is a negative feedback. We'll use slightly different versions of those diagrams as we go along, but this is an effect that tends to offset some of the original change. Yeah, we added carbon dioxide to the atmosphere, but we made more plants, and the plants took more carbon dioxide out of the atmosphere. That particular feedback is called the vegetation feedback, and it's one of a whole mess of feedbacks we're going to learn about in this lecture. The math of actually figuring out these feedbacks gets incredibly complicated. Your book tries to show you some examples and doesn't do very well at it. And their examples they're trying to show are the simplest ones. And so, you know, honestly, these models, these numerical models of climate that run on the supercomputers are in many ways our best and easiest way to understand what's going on in these feedbacks, rather than trying to write some equations that are going to describe these feedbacks. Now, before we move forward with this lecture, I want to just ask a couple quick questions to make sure we understand what's going on. Question 1, true or false? A negative feedback loop acts to amplify initial change to the climate system. Is that true or false? Choose from one of those two answers and get a little feedback before you move on to question 2.